Hello friends, welcome back to the channel. In our last video, we understood the concepts of Gateway API. Just to recap once again, Gateway API is not something completely new concept. It solves the same purpose as Ingress, but it addresses many of the limitations and the drawbacks of Ingress. So, we can say that both Gateway API and Ingress serve the same goal, exposing applications to the outside world using load balancer providers such as Nginx Ingress or Envoy. Now that the concept of Gateway API is clear, let's move on to the practical part. In this demo, I will show you how to use Gateway API in real-time scenario. We will be using our SCH students front-end React application, and instead of Ingress, we will be working with GatewayClass, Gateway and HTTPRoute. We have already set up a kubeadm cluster with one master node and one worker node. Let me take you to the master node and show you. Here, when I run the kubectl get nodes command, we can see we have one master node and one worker node, both running successfully because both are in the ready status. Now let's start with the first step, installing the Gateway API CRDS and Envoy Gateway controller. You can also use Ingress Gateway controller, but the Envoy Gateway controller is easier to set up and use, so we will go with that. Let me take you to the official Envoy Gateway documentation. So here under installation section, you will find the option install the Gateway API CRDS and Envoy Gateway controller. For this step, Helm must be installed because it is using Helm to perform these two installations. Let's quickly validate the Helm installation by running helm version command. So in my Kubernetes cluster, if I run helm version command, here we will see the output like helm version is 3.14.3 and we are good to proceed. Now let's copy the helm command from the documentation and run it here. Now let's break down this helm command so you clearly understand what it's doing. Here this -- create namespace. This flag creates a new namespace and with the name -n Envoy Gateway System. It creates a namespace named Envoy Gateway System. Within this namespace, Helm installs the Gateway Helm chart. This chart includes the Gateway API CRDS, the Envoy Gateway controller, and related deployments and services required for Envoy Gateway to function. So with this single Helm command, we are setting up everything needed to start working with Gateway API using Envoy Gateway. Hit enter. The installation is successful, and from this output we can clearly see the Envoy Gateway has been installed successfully. Let's quickly understand the important parts of this output. Here we can see name is EG. This is the Helm release name we provided while installing the chart. And this namespace is Envoy Gateway System. Envoy Gateway is installed inside the Envoy Gateway System namespace. And here status is deployed. This confirms that the Helm release was successfully deployed and its revision is 1. This is the first revision of the release. And last deployed, it deployed today itself. We can also see a note saying please be patient, Envoy Gateway may take few minutes to install. This means that even though Helm reports the release as deployed, the controller pods may take some time to become fully ready. The note section gives us helpful commands like helm status EG -n Envoy Gateway System and helm get all EG -n Envoy Gateway System. These commands can be used to inspect the release details if needed. Now let's validate what's running inside the Envoy Gateway System namespace. For that, we will run kubectl get pods -n Envoy Gateway System. From the output we can see the Envoy Gateway, this pod is ready. This ready one by one. This means the pod is healthy and ready. Status is running. Confirm that Envoy Gateway controller is up and running. This pod is the Envoy Gateway controller. It works very similar to Ingress controller. The gateway controller continuously watches the gateway and HTTPRoute resources, and once they are created, it configures Envoy according to route traffic to our applications. Since this Helm chart also installs the Gateway API custom resource definitions, let's validate that the CRDs are created successfully. For that, we will run the command kubectl get CRDS-A. From the output, we can clearly see that Gateway API related CRDs are available here. Most importantly, we can see GatewayClass CRD, Gateway CRD, HTTPRoute CRD. Along with these, we also see additional Gateway API related resources such as TCP route, TLS route, UDP routes, gRPC route, backend TLS policies, and other extended and experimental resources. This confirms that the Gateway API CRDs have been installed successfully as part of this Envoy Gateway Helm chart. Now our one step is completed. We have successfully installed the Gateway API CRDs and also Envoy Gateway controller. Now comes the next step where the actual DevOps work begins. At this stage, DevOps engineers are responsible for creating deployment, services, and other Kubernetes resources required to run the application. In our case, the deployment for SEH web app frontend application is already created. We are using React-based frontend application. And just like in real world scenarios, front-end applications are typically exposed to the internet because they are accessed by the end users from the outside world. Let me show you the deployment for our SEH web app front-end application. Let me run kubectl get deploy pipe grep SEH-web app. So from the output we can see that the deployment SEH web app deployment is running. It has two replicas and both are available. Now if I describe the deployment using kubectl describe command, describe deploy and then deployment name, we can see additional important details. Here we can observe that the container image is being used, this one. The replica set is there, which is responsible for creating two replicas. And here from replicas we can see 2 desired, 2 updated, 2 total and 2 available and 0 unavailable. We can also see labels type SEH frontend. These labels play a very important role because they help pods, deployments and services identify each other and manage traffic to the correct set of pods. Let's quickly verify the pods as well. For that, kubectl get pods pipe grep SEH-web app. From the output we can see 2 pods are running. Both pods are in running state. Each pod has 1 by 1 containers ready. This confirms that our SEH frontend application is up and running successfully. Now we need to create a service for our application. Before doing that, in our last video we had created a NodePort type service for our SEH web app frontend. So first let's delete that existing service. We will check the service using kubectl get service command. Here we can see NodePort service named SEH frontend NodePort service is available. Now let's delete it using kubectl delete service and then service name. Service is being deleted. Now let me take you to the Visual Studio Code to create a cluster IP type service for the front-end application. So that's my Kubernetes playlist, which is also available on GitHub, and under day 9 folder you will find all the service related YAML manifest. I have created a file named sch frontend cluster IP service.yaml. Like any Kubernetes object, this manifest has 4 main sections. The first one is API version. For service, the API version is v1. Kind, the kind is service only. Metadata is used to define the service name and labels. In our case, labels are not required, so we are only defining the name. So just give it name sch frontend cluster IP service. Now the spec section, this is the most important section. Here we define the port details, service type and selector. Under spec we define ports. Here the name of the port is HTTP and our application is running on 8082 port. Let's give the port as 8082 and the target port also 8082. This is the port inside the pod where the application is running, and this port is service port. Since this is the cluster IP service, we don't need to define the type is equal to cluster IP explicitly. Kubernetes will automatically assign cluster IP as a default service if we don't define type as cluster IP. Inside the selector configuration, as we know, service in the Kubernetes use selectors for the service discovery. So we copy the selector from deployment YAML. Go to the deployment YAML sch web app deploy.yaml. Here this label comes from the pod label section of the deployment. Let's copy it and we paste it in the selector field of the service manifest, that is type sch frontend. This allows the service to correctly identify and route traffic to the frontend pods. With this, our cluster IP service manifest for the frontend application is ready. The application will now be accessible inside the cluster on the port 8082. Since I am managing changes using Git, I will push this update to the GitHub repository. For that, git add git commit -m cluster IP service created for frontend app and git push. Inside the cluster, I have already cloned the Kubernetes playlist repository under /opt and code repo cd Kubernetes playlist and day 9. Let's do git pull here. And here we can see sch frontend cluster IP service.yaml is available, and apply the service manifest using kubectl apply -f then YAML file name. Getting the error unsupported value HTTP for protocol. If I do cat of this sch frontend cluster IP, it should not be protocol. Let me quickly correct it. Save the changes and push again. Inside cluster, do git pull again, and now apply the service. And now that cluster IP service is ready, the next step is to expose our application to external world. For that, we will need to create gateway class, gateway and HTTPRoute, and that's exactly what we will do next. Now again in the Visual Studio Code, under day 9, create a new file called gateway-class.yaml. I am referring to the official Kubernetes Gateway API documentation. This is the link, And I will also update all these steps and the links in my Medium page, and will share the link in the description box so you can easily follow along. On this documentation page, you will find sample YAML manifest for gateway class, gateway and HTTP route. Under gateway class, you will find a minimal gateway class example. Copy this and paste it into gatewayclass.yaml. And here is what this means. Gateway class defines which controller will manage this gateway by setting controller name, gateway dot envoy proxy dot io / gateway class controller. We are telling Kubernetes that Envoy Gateway is responsible for handling this gateway class. So any gateway or HTTP route that references this gateway class will be indirectly managed by Envoy Gateway. And let's rename it to EG. And this API version is gateway.networking.kubernetes.io and the kind is gateway class. Save it. Now let's create gateway.yaml. Here new file gateway.yaml. Again from the Kubernetes documentation, under a minimal gateway resource example, copy this YAML and paste it here and update it like API version is correct, kind is gateway, metadata just give it name Envoy Gateway, gateway class name that we have given Envoy Gateway, so make it Envoy Gateway, and the listener's name HTTP, protocol HTTP, and the port is 80. That's okay. Save it. So here gateway class name EG, this tells Kubernetes that this gateway should use the gateway class named EG, which is managed by Envoy Gateway. And listeners, this defines which port the load balancer should listen on. And here protocol is HTTP, traffic will be HTTP based, and the port is 80. The load balancer created by Envoy Gateway will listen on port 80. So this gateway represents the entry point, means load balancer for external traffic. Now let's create httproute.yaml. New file httproute.yaml. From the Kubernetes documentation, under HTTP route, under a minimal HTTP route example, copy the sample and paste it here. Now need to update it. API version okay, kind HTTP route, metadata just give it name, backend, spec parent reference that should be EG, host names just update it as schwebapp.sch.buzz. Rules matches, path type, path prefix that should be / kind service name, service name is, copy this and give the exact service name here. Application is running on 8082 and wait is 1. So here important explanation, parent refs, this HTTP route is attached to the gateway named EG. Host names, traffic will accepted only if the request host name is schweb.sch.buzz. I have already configured this host name in my Cloudflare. Rules are defined as an array which allows multiple routing rules if needed. Here matches, we are matching all requests with path slash. Backend refs, this is the most important section. Here kind service, backend is a Kubernetes service, name our cluster IP service, port 8082, traffic is forwarded to this port, wait 1 used for traffic splitting, useful in canary deployments. So in simple terms, when a user accesses the load balancer with hostname sh webapp.sch.bus and the path is slash, the request is forwarded to sh frontend cluster IP service on port 8082. Save all the changes and then push the changes. For that, git add dot git commit -m and git push. In the cluster, pull the changes, git pull, and my HTTPRoute, gateway and GatewayClass.yaml files are available. Apply the manifest one by one. kubectl apply -f GatewayClass.yaml, apply -f gateway.yaml, apply -f HTTPRoute.yaml. All resources are created successfully. Now check the Envoy Gateway namespace. kubectl get pods -n envoy gateway system. So here you will see Envoy default. This is the Envoy proxy acting as the load balancer. You can think of this as a reverse proxy or a load balancer, the component that receives external traffic and forward it to the service. If you are using a cloud provider like AWS, this could create an AWS ALB or another cloud load balancer. In our case, Envoy sets up the proxy internally. Now let's validate the service using kubectl get service and then namespace. Here we can see a service name Envoy default EG of type load balancer is created. This confirms that Envoy Gateway has created a load balancer service and the traffic can now flow from client to Envoy load balancer to service and then pods. Now at this point, all the components in the Envoy Gateway system namespace are up and running. We have two important pods. One is Envoy Gateway and another one is Envoy default. Envoy Gateway, this is the controller similar to an Ingress controller. Envoy default, this is the actual Envoy proxy which acts as a reverse proxy and load balancer. And when we created GatewayClass, Gateway and HTTPRoute, the Envoy Gateway controller automatically created a load balancer type of service for us. You might notice that the service shows external IP pending. This is completely expected. The reason is simple. We are running a kubeadm bare metal cluster. There is no cloud provider like AWS, Azure or GCP. There is no metal LB installed. Because of this, Kubernetes cannot assign a real external IP, so it keeps the external IP in a pending state. However, Kubernetes still exposes the service using NodePort, which is in our case 30,480. Now, let me explain this from a user's perspective step by step. When a user opens the browser and types shwebapp.sch.bus, this is what actually happens behind the scenes. First, the request reaches the node IP on port 30,480. This happens because in our setup, the Envoy Gateway service is exposed using a node port and the Kubernetes has assigned 30,480 as that port. Once the request hits node IP : this port number, it is forwarded to Envoy load balancer service created by Gateway API. From there, the request goes into the Envoy proxy pod. This Envoy proxy pod is acting like a reverse proxy and a load balancer. It is the main entry point for all external traffic. Now inside Envoy, the request is evaluated using HTTPRoute configuration. Here Envoy checks two main things, the hostname and the path. Hostname here is shwebapp.sch.buzz and path we mentioned as a /. If both hostname and path match what we define in the HTTP route, Envoy knows exactly where to send the request. Next, Envoy forwards the request to cluster IP service that we mentioned in the HTTP route backend reference. That cluster IP service then does its job of service discovery and load balancing, and finally routes the request to one of the front-end React pods. The React pod processes the request and sends the response back the same way, and the user sees the application in the browser. Let me show you one more important thing. If I check /etc/host, I have made one entry, this one. This ensures that the host name resolves correctly. Also, Envoy receives the correct host header and the request is routed exactly as defined in the HTTP route. Now when we run curl colon this port and we receive the HTML output of the React application. It proves that everything is working end to end. Let's also test in the browser. Since Cloudflare is already configured, we can see that published application route shwebapp.sch.buzz is pointing to our node IP colon port number. So when we access shwebapp.sch.buzz, the application loads successfully. So in this video, we understood Gateway API, used Envoy Gateway as the controller, configured Gateway class, Gateway and HTTP route, exposed a front-end application successfully, understood why the external IP is pending, verified real traffic flow using curl. This is modern Kubernetes networking, and this is why Gateway API is the future replacement for Ingress. If this helped you, like the video, share with your friends and subscribe to the channel, and I will see you in the next one. Happy learning!